Hello students, in this video we will learn about oscillations. Oscillations are known to you from your childhood. You can see the swing and you know how to swing on a swing. So it is not nothing new in it, and we have done these oscillations for lot many times. We are using it not only in our house, also in industry and everywhere. So that is very important concept that we'll be learning today. So what is basically an oscillation? Oscillation is the, say for example, to and fro motion or up and down motion. But if the some substance is or the particle is moving to and fro or up and down, is it a oscillation? No, it has to be periodic motion. That is very important. So periodic motion is important. Now what is mean by period? We know that if you take this swing to say extreme, normally we go to back and then we come back to this the original position, then we go to this direction and then we come back. Okay. So say for example this is one step, this goes to extreme, come back is two step, it goes to the front three step 3 and then come back as step 4. So all these 4 steps are completed in how much time? That is a period. That is what we call it as period. Okay. Of course you can measure the period from this extreme end also, and uh, at the center point or this extreme end. So it doesn't matter, it will remain same. Okay. Now naturally what happens is, say for example, let me just first draw this. This is a mean position, say M, mean position, and these are the extreme positions, say A and B, and let us give the name as O to this extreme position. So the distance from the mean position to the extreme position, that is called as amplitude. This is amplitude. So ideally the amplitude should remain constant. So let us give the name as say A to the amplitude. So we can have A on both sides, and ideally this will keep on oscillating for infinite time, but that doesn't happen. Why? Because of different forces like the friction. So for example, if someone is sitting here, so the air resistance will be one of the friction, so it may be air resistance. There could be the resistance at uh, the point where it is tied. Okay. In this image we are not able to see this, but it will be tied somewhere. Okay. So that around this fixed point. So here there will be friction because of uh, the moving parts, and that is one of the reason why it reduces, the amplitude reduces with time. So I can write at support we can have the friction. Now suppose we have this oscillation, and if the friction is somehow we make it 0, then what will happen? Then we can have the uh, the oscillations for infinite time. Now how we can show this oscillation? Okay, let us try to understand with this figure. Suppose there is a swing here like this, or you can take the simple pendulum also, but I will take the example of swing because you already know about it. You have played in when you were kid. Now this keeps on oscillating. Now suppose we have some kind of uh, thread here, or in two dimension we can have the cloth here, okay, long cloth. Then what will happen? Now if this is oscillating this way, obviously this cloth will go in this direction. But this part will go and this part will have the same position for short time. Why? Because it will be in inertia position, and then when it comes back, then it will start moving. So the force that will occur will be very small at the bottom, and it will be very high at the top, which is close to the chair, this chair. Now due to this, what will happen? The motion will be something like this, that the wave structure will be formed. This is two dimensional, remember. It is not one dimensional what I am trying to show you. Okay. This is the wave that you can have. Now this is very rightly connected with the oscillation and the wave, and then you can just show the oscillation. Okay. Let me very clear. So you can have, suppose, the oscillation like this. Of course, here we are talking about the standard oscillation, and the amplitude is remaining constant. We are just taking the ideal case. Now here, instead of now this amplitude, we will talk about the amplitude of the oscillation in terms of wave. Okay, this is not a wave actually, it is just the representation of the oscillation, how it is moving. Okay, now you can just imagine, suppose स्विंग मशीन, ओके, सिलाई मशीन जो होती है, तो उसमें this is bobbin, and in the needle is just jumping up and down, and then there is a cloth that is moving in this direction. Now you can consider this as time, so time is moving, and then this is just jumping up and down, up and down. How the thread moves? The thread will move like this, right? So this will be a kind of, not exactly, but kind of wave motion structure. So that is the oscillation, that is the oscillation in time. Okay. So oscillation and wave motion, and of course circular motion, they are connected with each other. We'll see in next topic, the circular motion is also connected with this. So how we can understand this? It is obvious that when you have this point, that means this is a mean position. So this shows the mean position. And then you go to say one extreme, that is obviously on one side, so it is considered to be positive, and the other side is considered to be negative extreme. So this is how it is changing. Okay. So suppose this is amplitude. Now, how do you write the force that you are applying to this say swing? So for the swing, when it is in motion, then the swing has, suppose, mass m and the velocity v, so that this is what we called as the momentum. And we know from the Newton's second law of motion, the force acting on any body is directly proportional to the rate of change of momentum. So normally what we do is we just say that the force that is defined by the Newton's second law of motion is F equal to ma, but that is a general case or particular case, not general, particular case, where the mass is not moving much or mass is not changing much. So what we can write is, say, let us consider the proportionality constant as 1, and then you just find out the derivative. Now if there is a case where mass is not changing substantially, so it is negligible, then you can just neglect this. Otherwise, you can write V dm by dt plus m dv by dt. That is what we write the equation for the force, general force. Okay, it may be in wave motion, it may be anywhere. But since the rate of change of mass is very less, we can neglect as compared to the other, and therefore then we get F equal to m dv by dt. Now that is what we find. So we can write this also as F equal to ma. So where a is the acceleration. Remember that I am writing the vectors at certain places, and you have to keep an eye on these vectors. Now this acceleration a is different and this amplitude a is different. So instead of getting confused, I will just write ACC. That is the acceleration. Of course, it should not be written in this way. Now this is the force that is acting on this swing when it goes to certain position and come back. Now why it come back? Why it come back? So that is what we call it as restoring force. Now, what is mean by restoring force? Suppose we displace some body, say point A, and then we displace the body to point B. Now naturally the body don't want to go to point B because of a quality of it is called as inertia. So nobody want to move from one place to the other place. So they are placed everywhere. Even human beings, they don't want to change anything. Whatever the routine may be, that is okay. So that is the inertia. Okay. And if you try to change the position or change the shape of the body, then it will resist and it will try to come back to the original position. And that is natural. That is what it is called as inertia. Unless you have the external force. Okay. Now because of this inertia, we will have the restoring force. So for example, if you are talking about the say swing, then the swing will try to come to its original position because of inertia. Now when it reaches to the mid position, it should stop here. Why it goes in this way? Because again now it is in motion, so it will remain in the motion. Now you remember the Newton's first law of motion. When the body is remains in the state of rest, or if it is in the state of motion, it will remain in the state of rest or motion. So initially it was in rest, it was forced to be in motion, it will remain in the motion. It will just try to remain in the motion. Of course, there are external forces which will reduce the amplitude, but now we are taking the ideal condition. So because of this inertia, we have the restoring force. And what is this restoring force? This F equal to minus kx. Now we can understand that the force is proportional to the displacement. That is okay. So this is the displacement. Okay. So maximum displacement is x max value will be the this value, that is amplitude. And you can have the displacement at different point like this. So depending upon that displacement, we will have the force value. The force value will change. It will not remain constant. Okay. Now, if we consider the force at any point, then why we are taking minus sign? It is because if you are moving in say this direction, say in one positive direction, the force will try to act in the opposite direction. Force will try to keep it in the initial position. So this is force and this is the displacement. Whereas if you take now in this direction, suppose it is going in this direction, Then this is the force, sorry, this is the displacement. So the object is going in, say, left hand side. So now the force will be acted such that it will try to restore the position, and therefore it will be always opposite to the uh, amplitude or the displacement, not amplitude, displacement. Clear? So this force is not inversely proportional, it is proportional to the x, the displacement, but in opposite direction. So this negative shows the opposite direction. It is not inverse, it is just the direction is opposite. So if the more you have the displacement, the more will be the restoring force. Clear? Now we just write down these two equations again. So let me write F equal to minus kx and F equal to m dv by dt, or you can just write velocity is dx by dt, and therefore dv by dt becomes d2x by dt square. So m d2x by dt square. So that is the acceleration, where it is a rate of change of velocity, and velocity is the rate of change of displacement. Now we just equate these two equations, say equation 1 and equation 2. So what we get is m d2x by dt square equal to minus kx, or we can write, since we don't want the coefficient of d2x by dt square as say m, we can take this m on the right hand side, and then we just take this minus kx on the left hand side also. So what we get is d2x by dt square equal to, sorry, not equal to, now we'll just take this on left hand side, so this becomes plus, and then k divided by m into x, which is equal to 0. Now this is second order differential equation. We can solve this very easily, and you might have solved all these type of problems in mathematics. But that is okay. That is the mathematics. What is interesting is this constant. What is k by m? So that is called as force constant, and we can replace this force constant by some another constant. In 12th you must have studied this, but why it was taken like that, let us discuss in detail here. Let us go back to again the equation, say f equal to minus kx. Now just talk about the scalar values. So what we get is, say, k equal to f by m with minus sign. So this is the force per, sorry, k by, sorry, not m, f by x. Okay. So this is force per, say, unit length. Okay. Now how can you find out the dimension of k or unit of k? Now we know the unit of f. Now unit is positive always. So it is 1 Newton divided by 1 meter. Now what is Newton? Newton is, say, 1 kilogram into meter per second square and divided by 1 meter. Now this 1 meter, 1 meter get cancelled out. So what we get is the unit of k is, say, kilogram and divided by second square. That's it. And therefore the unit of k by m, now here m is not meter, m is the mass, remember. So the unit of, say, uh, this k is kilogram per second square, and the unit of mass, it is in denominator, so this will be kilogram. So this get cancelled out, and therefore we get 1 divided by second square. Now what is this? This is nothing but, it is, say, I will just write like this, 1 by second and whole square. Why I am writing like this? Because we know 1 by second is the frequency unit and this is hertz square. So it has to be this quantity, k by m has to be the quantity which will be the square of frequency. And therefore I can write that k by m equal to say omega square. Why I am taking omega square and not omega? Because of the units. So the unit of omega will be hertz, okay, 1 by second, and therefore we are taken omega square, not omega. So you have used this constant, but probably you might not know that how it is working. Okay. Now let us uh, put this value in this equation. Okay. So what we get is d2x by dt square, d2x by dt square plus omega square x equal to 0, and that is the equation for the motion of say oscillator, any oscillator, a harmonic oscillator. Okay, let us stop here and just think how we can solve this equation and what will be the solution of this equation. So you can go to mathematics books or websites and then you can just find out the solution to this. See you again.